Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever with a little bit of Tom Petty and the Heartbreakers. We'll check back in with them a little later. Today, we are talking about probabilities using a calculator and how we can find probabilities if we have data that is distributed normally. So, should be a short vid. We'll see how it goes. Okay, so using the properties of the normal probability density function, we have considered probabilities in regions of width sigma to either side of the mean. And what we found was that we can find the probability of a random variable x by finding the area under the curve, which is finding the integral under said curve. So we can do that if we have a random variable x distributed normally with mean 10 and standard deviation 2.3. Notice the squared there. So if that's squared, then you know that's variance. If it's not, then you know it's standard deviation. Okay, so here they're saying let's find the probability that the random variable x lies between 8 and 11, and we could take that integral to find it. Luckily, we don't have to take that integral. We are going to use technology to do that because of the nastiness of the probability density function. So let's get to it, shall we? So, 3 examples we're going to do. If x is distributed normally, same problem that we just saw with a mean of 10 and standard deviation of 2.3, find these probabilities. So it's the probability that the random variable x lies between 8 and 11, including 8 and 11, and it doesn't matter. It's the same thing, greater than, less than, you calculate it the same way. That's another nice thing about this. What's that look like? Well, we just saw it on the previous page, but we're looking for the probability under this normally distributed curve. We're finding the area of this curve. And it's so easy. Let's take a look, shall we? So we're going to go to Menu, Probability, oddly enough, Distributions, and it's a normal cumulative. It's always going to be cumulative here because we're talking about continuous data with a normal distribution. I'll talk about this negative 9e to the 999 in just a second. But right now our lower bound is 8. Our upper bound is 11. Our mean was 10. And the standard deviation was 2.3. Oops. Look at that, I didn't tab. 10 and then 2.3. And voila, we get 0.476 to 3 sig figs. Please say yes on the 3 sig figs. So this is equal to, where's my pen? Where's my pen? Oh, it's white. That's why I couldn't find it. So that is approximately equal to 0.476. Okay, what about if it's less than or equal to 12? So I'm going to go back to the calculator, and normally what I might do is just scroll up and redo this, but I want to show you something. It has to do with that negative 9e to the 999. Okay, actually let's go back to this picture before I do that, just so we see what it looks like. Kapow. So we're finding the area under the curve from negative infinity to 12. And remember, as this curve approaches the x-axis, as x goes to negative infinity, it approaches the x-axis. Okay, so we have to have a way to tell the calculator, hey, way, way, way to negative infinity. Well, nothing can go to infinity, so our calculator, the best that it can do is, hold on, oh, distributions, so normal, cumulative, here we go. That's negative 9 times 10 to the 999th power. So that's as close to negative infinity as we can get. So that's negative 0.00000. That would actually be 998 zeros. That's our lower bound. Our upper bound is 12. Our mean, again, is 10. Our standard deviation is 2.3. Bing, bang, boom. Life is wonderful. We have 0.808. How great is that? So let's go ahead and put that in there. Approximately equal to 0.808. Could life get any easier for this right now? I don't think so. What about the probability that x is greater than 9? Okay. Well, we'll go back to the calculator. Oops, let's take a look and see what that looks like under the curve. Can you hear the losers outside making noise? I hope not. They're about to get Big Bertha. Okay. So this is what it looks like right here. To the calculator we go. So we're going, well, let me go back again. Sorry about that. We're going all the way under the curve. And remember, this is approaching 0. So we need a large number to approximate positive infinity, which is ridiculous because you can't really approximate it, but we have to get as far to the right as we can. So again, I'll go menu, probability, distribution, normal, cumulative, okay? So I'm getting rid of that so that our left bound is 9, lower bound. Our upper bound is positive infinity, but we can't do that. So we're going to do 9 times 10 to the 999. And our E button, EE right there, is just there, very easy. 999. Got it. 10. 2.3. Bing, bang, boom. Boom, shakalaka. That's 0.668. 2, 3 sig figs. And I mean, how easy was that? It was pretty darn easy. So that's about 0.668. Okay. Let's try some other ones. 2 more examples. In 1972, the heights of rugby players were approximately normally distributed with mean 179, standard deviation 7. Find the probability that a randomly selected player in 1972 was at least 175 centimeters tall. So what would that look like? Bam. Okay. So now I'm going to show you on the calculator. I'm just going to go up here at least. So that's greater than 175. So here I'm going to say from 175, I already have my approximation of infinity. They told me that the mean was 179, so I'll change the 10 here to 179. Oops, messed that up. 79. And the standard deviation was 7, so I'll change that out. 7. Bam. And so the probability would be 0.716. Approximately 0.716. Okay. And then between 170 and 190, let's get rid of that one, see what that looks like. Okay. And I'll go to the calculator again. I think I'll just copy it again so I don't have to go through the thing. So that was from 170, so change this to a 0, to 190. Then I don't have to change my standard deviation and mean. Very simple, very easy. I got to get rid of that 9.190, huh? There, okay, then that should do it. And I get 0.843. So that is approximately equal to 0.843. Okay, one more example. Actually, I'm going to stop the video and make a second one to do this because I don't want this to go on in case it takes a little bit longer. I don't want to go on for over 15 minutes. We're at 9, so let's check back in with our good friend Tom Petty. I have done I can't speak. I've done all the damage I can do here. For now, I am out.